तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So, we have been discussing the high electron mobility transistor. We have just gone through how it operates, the general idea. Today, we will discuss the, some aspects of the more aspects of the device, things like off voltage, that is equivalent of the threshold voltage of the MOSFET. Here, we call it as off voltage, the voltage that is required to turn off the device. The MOSFET, it is actually also considered as the off voltage required to turn off in a depletion mode type of device. And also we will see the IV characteristics and transconductance. So, the structure of this device, just to recapitulate, the generic HEMT, the first type of HEMT that was used was aluminum gallium arsenide heavily doped and undoped gallium arsenide. So, semi insulating gallium arsenide, undoped gallium arsenide, undoped gas, okay, and then the doped aluminum gallium arsenide, heavily doped N plus. So, this is the two dimensional electron gas region, where electrons are confined into the notch. And also on the top of this, you have got a metal semiconductor contact, which is a Schottky barrier, which actually is the gate region. So, just like in the case of MESFET, you have got the source and the drain, both as in the case of MESFET and MOSFET. You have got the gate. In the case of MESFET, you have a doped region between the gate and the substrate. In the case of MOSFET, you have a insulating layer between the metal and the substrate, that MOS. But in this case, you have a doped layer, and that doped layer actually should not be conducting. It should be depleted totally, otherwise current will flow through this. So, in a way it is more like a MESFET, a combination of MESFET as far as the top layer is concerned, and a MOSFET as far as the interaction between the gate and the channel is concerned. Because between the gate and the channel, in the MOSFET you have got the oxide. In the case of the high electron mobility transistor, you have got a depleted region, which acts as an insulator. This is actually the same diagram, just tilted it out and shown gate, drain, source, N aluminum gallium arsenide, spacer. Spacer is undoped aluminum gallium arsenide. It is also called as a setback layer. Then this is the two dimensional electron gas, undoped gallium arsenide, semi insulating gallium arsenide. Usually we show it in this fashion because that is the way you grow it. This fashion is easy for us to draw all the diagrams, because we move from the gate towards the drain like this. So, if you take as the axis, you can plot things in that. Now, this also suits us to draw the equivalent representation of this HEMT, because each device has got its own representation. This is the representation symbol. A circuit engineer can't be putting the entire device structure there, so they will put the symbol. You can see it is almost like the case of the MESFET or the JFET, except this arrow is not at the center, but shifted to the edge, indicating that you have the injection starting at the source end. Okay. Just to distinguish from the JFET and MESFET, this is the arrow. So, arrow indicates that the channel is N type. Like a p-n junction, p type and n type, arrow is from p to n. So, this arrow indicates it is an n channel HEMT. Okay. Now, This is actually when you draw the cross section through the heterojunction and band diagram. If the spacer layer is not present, you have aluminum gallium arsenide, and then you have actually got, this is actually the undoped, let me just go back to this. This is actually the undoped gallium arsenide. Okay. In between there is undoped aluminum gallium arsenide, but more accurately you can see this. The real structure is this. You have aluminum gallium arsenide doped, undoped aluminum gallium arsenide, and then gallium arsenide undoped. This is a spacer layer. Now you can see the energy band diagram, flat, okay, a depletion layer coming up, and these are the donors, and this is a notch, and from this edge right up to this edge there is a depletion layer. So, this region contains actually the ionized acceptors, because it is lightly doped p type, undoped actually, and also the charges at the notch, that will contain the charges. Okay. Now, if you see further, just whatever you have been telling, we put it in words here. The electron concentration in the channel region is controlled using the gate control with the Schottky barrier. See, for example, if you take it here, there are electrons here, there is no gate control. You have n type material, doped, undoped layer, which is almost p. So, there are charges collected here, you have no control. To control that, you must put a gate here. Okay. So, that is what is said here. You have a Schottky barrier, which is acting as a gate. The metal regions with the source and drain contacts are similar to ones in MESFET or MOSFET for that matter. The drain current flow due to electron transport through the N aluminum gallium arsenide should be avoided. The right at the beginning, let me go just quickly go to that. See, the current flow from the source to the drain should take place only through the electrons in the notch, because they are the high mobility electrons. These electrons, there are electrons plenty here, but the mobility of these electrons is low because doping is high. You do not want what is said in that sentence is the current transfer from the source to drain should not take place through this layer, it should take place only through this layer. So, that is possible by depleting this particular layer, and that can be depleted using this gate. So, the gate will serve the purpose of depleting this gallium arsenide layer. Gallium arsenide layer will be depleted due to two reasons. One, due to the gate depletion layer, other one due to charge transfer from the L gas to the gallium arsenide. So, the depletion layer is here is the result of two junctions playing on that L gas layer. One is this p-n junction, other one is Schottky junction. So, what we say here now is the drain current flow due to electron transport through the L gas layer should be avoided by ensuring that this layer is fully depleted under the gate region. So, how that is achieved? In fact, what I have shown here is L gas n type, undoped gallium arsenide. I have not shown the spacer layer, it is understood that it is present there, it is very thin layer. So, doped layer and undoped layer. Now, you can see the gallium arsenide layer is fully depleted, and VGS, I am not able to show it here because it is just through the gate layer the cross section is drawn. VGS is between the gate and the source. Now, you can see this portion of the energy band diagram. Conduction band here dips down because of depletion, and also there are accumulation of electrons, that is the notch, and on this side you can see that there is a depletion layer. Just notice that the energy band diagram here dips down, means the field is in that direction. Okay. The field is in that direction, whereas the energy band diagram here has a minimum, that means the potential is minimum there, which means the electric field is 0. Okay. d phi by dx is 0, okay, and phi is minimum. So, d phi by dx is actually the electric field, but throughout the region there is electric field. You say that because the energy band diagram is bending throughout. Okay. Now, I will just go to this board and see how that is possible. If I take the N aluminum gallium arsenide, okay, let me just put it on outside. And this is gallium arsenide, P minus, very lightly doped. Okay. Now, what you say is you apply, you have a gate here, onto which you apply voltage with respect to source. Source is connected to the channel. The N plus layer goes all the way up to the 2-dimensional electron gas you have seen in all the diagrams. So, you have got electrons here, you have got depletion layer here, you have got a depletion layer here, which I represented by this plus, just put 2 plus there, but the number of charges present there, because this is very heavily doped. Okay. Now, this part of the depletion layer is part of the p-n junction. So, electric field is in this direction here, all the field lines originating here terminate on that side. Now, the Schottky barrier, okay, if I apply negative voltage to the gate, to the built in potential itself, there will be depletion layer. Built in potential, okay, plus here minus here, there will be electric field from this side to this side. As I keep on increasing the gate to source voltage, this depletion layer keeps on moving. At a particular voltage, the entire layer will be depleted. Okay. So, you have got this keeps on moving. So, let us just plot the electric field. Over here, the electric field is 0 here. Okay. So, the electric field is like this, steeply going up, because heavily doped, and from there onwards falling down like this. That is the electric field distribution in the p-n junction, all of us know it. And on this side, how will the electric field be? If the depletion layer is only up to this point, electric field will be in this direction, minus plus, built in potential is plus here minus here, electric field lines will be in that direction. So, you will have the electric field actually like this. The slope of this electric field will be parallel to that, the electric field slope depends upon doping concentration, it is same. So, you will have actually a line like this at this point. Suppose the depletion layer moves further, when will it move? I keep on increasing the voltage negatively more and more. This when you apply no voltage, when you do not apply voltage is like this. If I increase this VGS, the depletion layer will keep on moving. At a particular voltage, what will happen will be, both the depletion layers will merge. That is, this is 1 corresponding to this 1, this is a curve. Now, when this depletion layer merges here, I am just drawing it again on this will go like this, this is 2. line 1 corresponds to the case when there is depletion layer is at position 1. Electric field line 2 corresponds to the situation when the depletion layer is at 2. In the sense, both the depletion layers have merged now. You can see that at a particular voltage VGS, the total depletion layer, total L-gas layer is depleted, okay, but the charges are present here. The charges are present here, because that part you have not disturbed now so far. All that was happening was to the minus charge that you put here, plus charge was coming from here. Now, what will happen if I increase this voltage negatively further? See, at this point you have not disturbed the p-n junction conditions, because interaction was between the aluminum gate and this n plus layer. Okay. Hereafter, if I increase the voltage, you will encroach into this p-n junction, because when I change the voltage further, it will look forward to the plus charges. Okay. Where will the plus charges come from? It can come if this moves further down. See, here up to this point, up to that point, all these are plus. All these charges belong to this Schottky, and these charges beyond this point 2 belong to this p-n junction. Now, if this Schottky barrier needs more positive charges, the only way it can happen is by this depletion layer of the Schottky barrier encroaching into this region. It moves into this region. That means, some of the positive charges from here participate in the Schottky barrier. Okay. What happens to depletion layer here then? This is the point at which the electric field is 0, because from here it is in this direction, from here it is in the right hand towards the right side. So, if the depletion layer moves further down, what happens is this point moves there to point 3. Okay. It will move to point 3. And what happens to this? If this moves to point 3, the additional charges from here belong to the Schottky. That means, the plus charges which belong to the p-n junction have been reduced. It has been taken care of by this. So, this is the minimum point in depletion layer. Now, from there it goes up like that. I just over amplified it. It goes up like this, and then what happens to this electric field here? Like that, parallel. Okay, what has happened now is, physically what has happened is, we have argued it out by pushing the depletion layer towards that side, so that the depletion layer belonging to Schottky barrier has widened, the depletion layer on this side belonging to the p-n junction has reduced because of that. If it has reduced on this side, charge on the depletion layer of p-n junction has got reduced, plus charge. That means, minus charge on this side has got reduced. So, depletion layer has collapsed. So, the potential variation from here to here, it was area under this curve. The new situation from here to here is area under this curve. That means, the notch which is there from here, or this potential variation from here to here, has got reduced. Okay. What is the meaning of that? If the potential variation, we can just go into that afterwards, we will see. So, ultimate result is the potential from here to here has reduced, potential change. When you draw the diagram, we will see it further. Now, you can view it in a different way. What we have seen now is this is getting pushed in this side, telling that the minimum point or 0 potential, the 0 electric field point has shifted to the right, or the minimum potential point has shifted down to the right. But actually what happens is, when you put minus charges here, if the whole thing is depleted at this point, the whole thing is depleted. if I put a minus charge here extra, that is if I increase VGS, where will the plus charge come from? From the other end, because it is as if there is an insulating layer. When I put a minus charge, a plus charge should come from here. How can the plus charge come from here? By uncovering the depletion layer, because this has got plus charges like this. It moves in this direction. See, plus charge appears here means what? The depletion layer width has got reduced by movement of the positive charges towards that side. So, that is exactly what has happened here. This has moved, depletion layer width has reduced, because the plus charges from here due to the holes has come up here. So, this is another way of looking at this. Ultimately, what has happened is the depletion layer on this side has reduced. As a result of that, what will it reflect upon? Let us go back to this diagram now and see the explanations are, I hope it is clear. The gate now gains control. The gate gains control over this region, because the entire layer is, once it is depleted, it gains control over this. And when it gains control over this, the depletion layer collapses. So, what happens? Let us just draw the diagram now. In fact, let me just go back to this and show you. See, this is the diagram that we have been seeing. From the left hand side, you can see the conduction band drops down like this. That is because this is the region where the field lines are from the semiconductor to the metal, plus here, minus here. This is a region where electric field is from here to here, plus to minus. Okay. So, wherever the potential is positive, conduction band goes down. So, the potential, okay, it is plus here with respect to that point. That is why the energy band diagram is dipping down. Minimum potential, this is the situation that is shown there. Minimum potential corresponding to 0 field, and from there to left hand side, field is from right to left, from here it is left to right. Okay. Now, see the charges which are present on this side. Below this, you have got all the charges plotted. Entire region is depleted, that is the Q and D plus charges of the depleted layer, and this is the negative charge on the gate. So, corresponding to the negative charge of the gate now, you have got plus charges here, and corresponding to some plus charges from here, you have got negative charges here, due to this charge in the notch and also depletion layer charge. All this is negative, part of plus charge is interacting with this, part of plus charge is interacting with this negative charge. Okay. Now, at this point, if I increase negative charge here, what happens is, as we have just now discussed, this potential barrier reduces. If this potential barrier reduces, surface potential here reduces, what happens to the charge here? It becomes less n type, less band bending. It is like an inversion layer. The band bending is more electrons in the inversion layer. The band bending is less electrons. So, by increasing this voltage more negatively, you actually have a reduction in the surface potential, reduction in the potential change here, which is reduce these electrons here. Okay. And depletion layer also collapses because potential is reduced. So, what you are telling now is, if I increase the voltage beyond certain point, you will have control over this negative charge through the gate. Okay. Let us go further down. See, this diagram makes it further clear. Under thermal equilibrium conditions, I have drawn the energy band diagram for this portion alone, p-n junction alone. So, under thermal equilibrium condition, there is no depletion layer here in the aluminum gallium arsenide, whereas the depletion layer is present here and depletion layer present here, and there are electrons here. If you recall, when we discussed the heterojunction, we said that the band bending here is more than the homojunction by an amount equal to this delta E c. This is equal to that. That is not to scale. Whatever discontinuity in the conduction band is here, that extra potential will be there in the heterojunction compared to homojunction. Now, if I apply forward biasing to this plus minus, see what is the polarity of this potential? Plus here minus here. So, if I apply forward bias equal to delta E c by q, the total potential will be reduced by that amount. Okay, it is just like this. If I have a p-n junction, okay, if I have a p-n junction, p minus and n plus if I have, depletion layer is almost here. So, you have got, this is true in the case of homojunction. I have the depletion layer, you have the depletion layer here and slightly small bit there. Okay. So, in fact, that is what you have shown there. You have okay. I am showing only that portion, that is the potential. Here there is practically nothing. In fact, what you will have will be further down here in the homojunction, but in this case you have got like that delta E c. Now, when I forward bias this and this polarity here is plus here minus there, built in potential, which is delta E c by q higher in the case of heterojunction. If a forward bias, you superimpose on that, a voltage is opposing that. So, that actually comes down. That comes down in the same fashion that I have shown there, and that quantity is actually delta E c by q. What about here? That also slightly fall down. It is slightly fall down because charge is very high there. So, you will not notice the changes in depletion limit so much. So, mainly whole entire effect is felt on this in a n plus p diode. So, what we are trying to point out is, by applying a forward bias like this, I am reducing this potential radiation, potential change. So, therefore, the band bending is reduced, therefore, the charge here is reduced. See, for example, if you take a p type semiconductor, okay, take a p type semiconductor, Fermi level is there, okay, under thermal equilibrium conditions, no depletion layer, but when the depletion layer comes up, what happens? Fermi level is there, sorry. So, all that happens is you have to visualize that how much it is n type depends upon how much is bent. If it bends less, it becomes less n type. In this case, actually it is similar argument. If it bends less by forward bias, number of electrons in notch are less. So, what we are telling is, if you apply voltage equal to delta E c by q across the junction, you will be able to reduce the charge practically to 0, because in the homojunction, when its VBI is ND VT logarithm of ND NA by NI squared, charge there is minimum, but that extra charge is present at the notch corresponding to delta E c by q potential change. I reduce that potential by applying forward bias, charge is brought down to very small value. Okay. In other words, I can reduce this charge practically to a very small value by reducing this barrier by an amount equal to delta E c by q. Whatever extra delta E c was there in the conduction band, I remove it by applying forward bias across this charge will be reduced to 0. If the charge is reduced to 0, what happens to drain current? Let us go back to this diagram. Unfortunately, I have to keep on going back to that. see the charge here is reduced if the potential drop across the forward bias is delta I c by q, and the entire layer is depleted. So, when I apply voltage between the drain and the source, there are no electrons in the depletion layer, and in this charge layer is just very small layer. It is just like saying it is just about to invert, just inverted sort of thing. So, you have minimum electrons there. So, current will be 0. That means, what you are telling is you can turn off this device by applying voltage across the gate and the source, such that there is a forward bias voltage across the junction, which is equal to delta I c by q. What should be the voltage across this aluminum gallium arsenide layer, such that the entire thing is depleted? In the MESFET we saw a term called as pinch off voltage. Pinch off voltage is actually the total potential across the channel region in the MESFET, that is V p 0, which will actually deplete the channel completely. Okay. Let me just go back to that now. I hope these points are clear. So, the MESFET, the N layer is fully depleted when VGS is equal to VGS1, I will call it VGS1 equal to threshold voltage VBI minus VP0. Okay. When it is equal to VBI minus VP0, channel is fully depleted. What is VP0? VP0 is A square divided by twice epsilon r epsilon 0. Okay. So, now what we have got is a situation where you must have a voltage across this entire layer, that is, let us neglect the drop across the spacer layer because it is very thin and it is undoped layer. So, total thickness is A here. So, when the gate voltage, let us forget for the moment that this layer is present, the entire layer will be depleted when VGS equal to V threshold voltage of MESFET, that is VBI minus VP0. Okay. Now, what we are looking for is what should be the gate voltage that I must apply, so that not merely this layer is depleted fully, electrons here also are absent or it is just about to conduct. So, what is the total potential of this point and this point? The total potential is the voltage that we must apply to the gate to deplete the N layer completely, plus the potential that must appear across the junction. Okay. So, let us put it down like this. Let me just draw that like this here, because it becomes clearer. So, if I have that is N gas. Okay. What we are looking for is what should be the voltage that I must apply to the gate, so that this entire layer is depleted. Okay. We know that if the voltage required to deplete the entire layer is equal to VBI minus VP0. Okay. VP0 is the total potential barrier from here, but if there is already VBI, the voltage required is VBI minus VP0. I think you just forgotten the formula that is used for the MESFET. This portion equivalent of MESFET. Okay. And what is the potential that you must apply here? So, this is minus plus VGS1 to deplete that. Okay. Okay. Now, over here the applied voltage appears across this plus that. Forward bias. So, this voltage is V B I minus V P 0 VGS. So, VGS is equal to VG, okay. V off is VGS 1 minus because this is plus minus here VGS 1, though it has this polarity we have put here, but we are putting it as a plus voltage. So, VGS 1 threshold voltage of the MOSFET portion is V B I minus V P 0. You must apply extra voltage with negative polarity here, that is minus plus and minus plus here. So, if I apply V off equal to VGS 1, that is V B I minus, so V off is V B I minus V P 0, okay. That is the threshold voltage of the MOSFET portion. The voltage that you must apply to the gate, so that entire gas is depleted. Okay. And to remove the charges from here, you must apply a negative voltage with respect to the substrate. So, I am just subtracting minus delta E c by Q. So, that is actually the voltage that you must apply to the gate to turn off the HEMT, to ensure that electrons are just barely minimum. There will be still some electrons, but minimum not sufficient for conduction. It is like just like the MOSFET. In a MOSFET, you say threshold voltage is the voltage at which the MOSFET is turned off. Okay. You actually take that voltage as the voltage at which surface potential is twice phi f. It is equivalent of that. There are some electrons, but beyond that point, if you increase the voltage, okay, positively, you will have more electrons coming up. Okay. V of this is very small, it is equivalent of threshold voltage. Now, if I increase the gate voltage with the substrate positively, let us give some numbers. V B I minus V P 0, let us say, is equal to 0. Okay. V B I minus V P 0 is 0, it is possible. Pinch off voltage equal to 0.8 volts, V B I is 0.8 volts, that is 0, just to give an idea. And delta E c is 0.3 electron volts. What is the off voltage? 0 minus 0.3 volts. So, the threshold voltage of this, which you call it as off voltage, is minus 0.3 volts. Okay. Now, if I bring it from negative to positive, what happens? If I bring it from negative to positive, it will appear across this straight away. Or you can say, if I bring it from negative to positive, the coupling will be between the gate and the channel, because there is the inversion layer. Like in the case of MOSFET, I can increase the charge from here onwards, just in the verge of inversion in the case of MOSFET, by applying voltage to the gate over and above the V off. So, the charge here now can be calculated as gate voltage minus V off. Supposing this is, let me give some other example. Supposing V P I V P 0 is 0.4 volts plus 0.4 and this is 0.3. So, V off is 0.1 volts plus 0.1. Now, if I apply 0.3 volts here, 0.3 volts minus 0.1 volts. 0.2 volts appears across this, interaction is between these two straight away, negative charge. So, when I change this voltage, negative charges will be brought in here, because there is a direct connection between the gate and these points. So, you are applying a voltage between the gate and the inversion layer in the case of MOSFET. Similarly, the additional voltage above the off voltage or threshold voltage, whatever you apply will appear into this layer. What is the relationship between the charges? Okay, let us just go back to that now. In the case of MOSFET, see, always it is easy to compare with the MOSFET, because it is almost like a MOSFET. The notch in the case of MOSFET is obtained by means of the oxide. Here notch is obtained by means of the heterojunction. The channel E is actually equal to C oxide into VGS minus C threshold. If there is no drain current means actually we subtract the drop in the channel from there. In MOSFET, this is because whatever voltage is there over and above threshold voltage interacts between the gate and the channel. So, C oxide into the extra voltage gives extra charge in the channel. Same way here, instead of C oxide you have got, instead of C oxide you have got the capacitance of this L gas layer, which you can call it as CS, like in the case of MOSFET. So, MOSFET, just notice the only difference between S and D, one is MOSFET, other one is MOSFET, okay, because modulation doped. Q channel is, instead of C oxide you will have, see, in the case of MOSFET you have metal, oxide, semiconductor. In this case you have got metal, aluminum gallium arsenide which is fully depleted, and the semiconductor. It is inversion, you have got the notch charge. So, coupling is between these two. Why I am bringing this analogy is, which one is exactly same as MOSFET hereafter. All that you have to know is, if I apply voltage V off equal to VBI minus VP0 minus delta EC by Q, that is the threshold voltage, you will turn off the channel. Whatever extra voltage you apply above that will couple between the gate and the channel. That is all what you have to see. So, this will be CS into just notice the difference. You call it as threshold voltage there, you do not want to call it threshold voltage, actual threshold voltage, we call it off voltage, voltage that you must apply to turn off the channel, because there will always be inversion, there will always be a channel there because of the L gas layer. So, what is CS? Epsilon r epsilon 0 divided by, we call this as A, the entire layer is A, that is B, per centimeter square, charge is per centimeter square, all this we are talking about by that. So, now if we have seen, from what we have seen, it is clear that this entire device would behave like a MOSFET if this is conducting. Now, that is not what you are looking for. We are trying to solve that problem of that heavy doping here. So, if the entire layer is depleted now, and when the charge is present here due to the gate voltage, the charge is present which is controlled by means of gate voltage, you have the current through this entire shaded region here, yellow color here, that is the 2-dimensional gas, electron gas. So, that is actually controlled by the gate voltage, exactly the same way as the MOSFET. So, all that you write is the charge here is gate voltage minus the V off into the capacitance of this layer. In fact, that would include the capacitance of doped layer and this undoped layer. What you are telling is this layer must be kept small as possible, but this layer is needed so that the electrons here do not see the dopants. The electrons are not in the vicinity of the dopants. So, the Coulombic scattering is removed by putting undoped layer here. But you can see if you put the undoped layer here, immediately what happens? The thickness of the layer slightly goes up. If the thickness of this layer slightly goes up, the CS slightly falls down. For a given gate voltage, the charge falls down. You can immediately see that if A goes up, CS falls down. If CS falls down, the charge falls down. That is, for a given change in voltage, the charge is less if CS is smaller. That means, for a given change in voltage, the change in current is small. That means, GM will fall. So, what we are telling is putting this layer here is good. Introducing this spacer layer is good to improve the mobility of these electrons here, but you can't make the layer thicker and thicker. If you make it too thick, the entire A, which decides the capacitance which couples the gate to the channel, actually will go down. It will actually affect the current, it will affect the transconductance. You are looking for devices which have high current capability and high transconductance. So, that is why this layer is invariably chosen as about 20 angstroms, 40 angstroms are the most. Okay, I think I have been discussing most of the things. Now, everything is put in some form of diagram. I can just zip through these diagrams now, because everything I explained in the board. So, this is what where we just stopped and went to explain everything in the board. Now, you can see that the charge here can reduce by applying more negative voltage here. Okay, this is a situation where the entire thing is just depleted here. You increase the voltage by an amount equal to minus delta I c by q, the charge will go down to minimum. That is off voltage. Okay. So, this is what we have done here. We apply a forward voltage across that layer to bring the charge to 0. Now, this all we have just gone through. The voltage VGS1 required or V threshold voltage of MESFET is VBI minus VP0, okay, where VBI is the built-in potential of the MS contact, metal semiconductor contact. See, now, please do not confuse between VBI of PN junction and the metal semiconductor. There are two different things. So, built-in potential of the Schottky barrier is VBI, which will be about 2/3 of the EG if that is Fermi level pinning. Okay. And Vp0 is pinch off voltage, which I have written down there, equal to Q and D A squared by twice epsilon epsilon 0. That is Vp0, which you all are very familiar. Doping in the N plus layer, A is thickness of the layer. A is the L-gas layer thickness and Nd is the dopant density of the layer. Okay. Layer is the dopant density of the layer. Okay. Okay. Now, what we have been telling is all that we explained is written here in words, that if VGS1 will deplete the entire layer. So, any extra voltage that you apply across the gate source deplete layer of the metal in the region as shown below. Yeah. I have drawn all the diagrams on the board. So, this is just summarizing the whole thing. See here, this portion of the depletion layer belongs to the gate. This portion of the depletion layer belongs to this PN junction. So, if I apply extra voltage, the depletion layer will move down and this depletion will collapse and the charge here will reduce. That is what we have been telling right through. Okay. Redrawing it between neat fashion here. And this is actually the electric field just when the depletion layers merge if you increase the voltage further negatively, this point will move to the right and this point will move to the left. This potential is reduced. So, additional negative voltage increases VGS and this will widen the depletion layer belonging to Schottky barrier. What I mean is, this is the depletion layer belonging to Schottky barrier. Any more negative voltage actually will widen this layer which belongs to the Schottky barrier, and it will reduce the depletion layer width here. That is what is said there. Narrow down the depletion layer width of the heterojunction. The band bending reduces means electron concentration in the channel gets reduced. So, what we said now is, as a result, you have got V off equal to VBI minus VP0 minus delta IC by Q. Please note now, VBI is the built-in potential of the Schottky barrier, VP0 is the pinch off voltage of the N plus layer, and this is the forward voltage which appears across the junction, because that is the voltage that is required to forward by the junction to bring the electron concentration, not actually 0, but very small value. So, now what will you say about the IV characteristics of this device? Exactly like the case of MOSFET. So, once you say that the charges in the inversion layer is that in the case of MOSFET, when the VDS equals 0, the charge in the channel of the MOSFET is this, the equations governing the MOSFET and MOSFET will be same thing, except replace C of the CS. So, if you get a square law in the case of a MOSFET, you will get square law in the case of MOSFET also, provided of course, there is no velocity saturation, and you get this equation. Okay. Notice we have replaced C oxide by CS. See, in the case of MOSFET, you have the oxide which is actually the coupling the gate to the channel, whereas in the case of MOSFET, you have the depletion layer whose capacitance is CS, which couples the gate to the channel. Transconductance is delta ID by delta VGS. So, 2 cancels and you get this one. Now, you can see you get better and better transconductance if you have got better mobility. Okay. And since gallium arsenide layer is undoped, no scattering due to impurity scattering. So, at room temperature itself you will get about 8500 centimeter squared per volt second here, and CFS you would prefer to keep it large, keep GM large. Compared to MOSFET, CFS will be large compared to C oxide for same thickness, because C oxide is formula is same as this, except this is epsilon oxide. In the case of MOSFET, this is 4, this quantity is 4. In the case of gas, this quantity is almost 12.8 to 13, about 12.8. So, about 4 times or 3 times more in the case of HEMT. Okay. This is about 3 times larger than that of the MOSFET C oxide. Epsilon 0 is same thing. A we are taking same for comparing for the same situation. This will have CS which is about 3 times larger. Okay. So, when you go to the HEMT, you get transconductances which are larger due to higher mu n. In the case of silicon, how much is mu n? Surface scattering is dominant, about 1000 centimeter square per volt second. In this case, it is about room temperature about 8500, 8.5 times larger, and CFS is about 3 times larger for say same A, same thickness. So, it is at least about 25 times larger transconductance. The transconductance is 25 times larger, cutoff frequency will be larger by the same factor for same capacitance, because cutoff frequency is GM by C. That is the figure of merit of all these FETs. So, you will have much higher frequency of operation for these devices. You can get enhancement type or depletion type of MOSFET. Okay. How do you do that? V off. Okay. ID versus VGS, enhancement, ID versus VGS, the depletion type, enhancement type. This is V off positive, V off negative. Okay. Enhancement mode, depletion mode, and you can adjust the V off by adjusting what? V off is combination of, I think I will just discuss this in the next lecture. V off is determined by VBI minus VP0 minus delta IC by Q. Only parameter that you can control there is VP0. So, doping and thickness has to be adjusted to adjust. I will take on from here in the next class, but you can see the most important thing to note is the VP0 you can control, the doping and thickness you can control. In fact, you want to keep two things to be done. CS you must keep as large as possible. So, you must reduce the thickness, but okay. To change the V off, you must change the doping. So, there is some sort of optimization involved in these devices. Some of these aspects I think I will discuss in the next lecture, okay, because optimization parameters are there. Okay.